In our previous videos, we discussed the basics of vectors, and we also talked about the inner product of vectors and the concept of orthogonal vectors. In this video, I'm going to talk about the inner product of functions and the concept of orthogonal functions. And hopefully in the next several videos we should be able to cover the basic materials, and then we will transfer to the Fourier series and from there to the partial differential equations. So here is the structure for the rest of this video. We're going to start with the definition of the inner product of two functions. We will then introduce the concept of orthogonal functions, and at the end we will try to see if there is any geometric significance when we talk about the orthogonal functions. Let's assume we have two functions f1 and f2 that are defined on an interval a to b, and these two functions are piecewise continuous. So first let's talk about this term, what it means for a function to be piecewise continuous. So that basically means that your function can have some discontinuity, but the number of those points, those discontinuous points, needs to be finite. For example, if you have a function, let's say this is a all the way to here b, so your function can have a discontinuity like this somewhere here, but it's still considered piecewise continuous. Why? Because, for example, from a all the way to here c, so this function is continuous over a to c and c to b, so it's still considered piecewise continuous. And it can be even worse than that. For example, it can be having more discontinuity than just one. For example, if this is interval a to b, your function can be something like this. For example, it can be having a discontinuity here, and then another one here, another one here, another one here, and something like that. So for example, this function that I have shown here is discontinuous on here, on this point, here, here, and here. But we still consider this function to be piecewise continuous just because we can find some subinterval on which the function is still continuous. In other words, the number of discontinuity is finite, so it's not infinite, right? So most of the functions that we are dealing with are practically piecewise continuous, so this is a kind of not that strict condition for this definition. So if we have two functions with this condition, then this expression that is shown here, this integral over the interval a to b, is going to be the inner product of two functions f1 and f2. And by analogy of the vectors, we show the inner product of these two functions in a parentheses, f1 and f2. So if you remember, for example, if we had two vectors like a and b, we would show its inner product by a dot b or a and b in a parenthesis, right? So for the inner product of two functions, we use this notation shown here. Using the parentheses, we put f1 and f2 here, and that just means we refer to this integral of f1 times f2 over the interval a to b. Now let's take a look at a very simple example here. We have two functions, f1 equals x and f2 equals x squared on the interval 0 to 1, and we want to find the inner product of these two functions. In order to find the inner product of these two functions, we don't really need to draw these functions on the coordinate plane. But to give you some kind of insight how these functions look like, I would like to draw those functions first. So here is the both functions f1 equals x and f2 equals x squared shown on the same coordinate plane, and we are interested in this specific interval here for this example from 0 to 1, and we want to find the inner product of f1 and f2, so we just need to multiply f1 and f2 and find the inner integral of that product over the interval 0 to 1. So by definition, the inner product of f1 and f2 is going to be integral of f1x times f2x dx on the given interval, which is 0 to 1 for this example. So that's going to be integral from 0 to 1. f1x is going to be x times f2 is going to be x squared dx, which is going to be integral from 0 to 1 x to power 3 dx. So the integral of this function x cubed is going to be 1 over 4 x to power 4, and from 0 to 1, which is going to be 1 over 4 1 to power 4 minus 0 to power 4, which is going to be 1 over 4. So it's very important to emphasize here that when we talk about the inner product of two functions, there are a few elements in that definition. One of them is the function f1, the other one is the function f2, and the other one is the interval. So inner product of f1 and f2 is not really independent of the interval. In fact, it can very well change from one interval to another one. So it's important to know which interval you are defining the inner product of those two functions on. Now we get to the this new concept of the orthogonal functions. By definition, two piecewise continuous functions f1 and f2 on the interval a to b are called orthogonal if their inner product is 0. So if you remember from the basics of vector, we've said that two vectors like a and b are orthogonal whenever their inner product is 0. So if inner product is 0, then we call those two vectors to be orthogonal. Right? And similarly here, if we have two functions with the inner product of 0, by analogy we call those two functions to be orthogonal. So in other words, if inner product of f1 and f2, which is this integral, is 0, then we call those two functions to be orthogonal on that specific interval. Orthogonal functions on a to b. So it's very important again to emphasize here that this interval is very, very important in the context of functions. In the context of vectors, we didn't have such a thing. Two vectors could be either orthogonal or not, depending on the value of their inner product. But when we talk about the functions, it's very important to define what interval we are talking about. So for example, two functions can be orthogonal on a given interval, while they can be non-orthogonal on other intervals. So it's very important. And the other thing is that for the two-dimensional and three-dimensional spaces, when we had two vectors orthogonal, that would just simply mean those vectors were perpendicular, right? So the term orthogonal and perpendicular were kind of synonym for the vectors in two and three-dimensional spaces. But in the context of functions, there is no really geometric significance when we talk about two functions, f1 and f2, and we call them orthogonal. It's just a definition. That means that this integral of the product of those two functions on interval a to b equals 0. That's it. You may wonder why is that important then if there's no geometric significance, and you're going to soon realize that functions with this property are going to be very, very helpful, and they're going to provide some really powerful tool when we want to solve the partial differential equations. So since they are very important, then they deserve to have a name, and by analogy of the orthogonal vectors, we call such functions orthogonal functions, although there is no geometric significance behind that term. Now let's take a look at this example here, and we want to see if f1 and f2 are orthogonal on this interval, -1 to 1. So these functions f1 and f2 are the same as we considered before in our previous example, but the interval now is different. It's from -1 to 1. So let's see if they are orthogonal. We need to find the inner product of f1 and f2, and that basically means that we need to calculate the integral of their product over interval -1 to 1. So, and if we do that, we get -1 to 1, f1 is just x, f2 is x squared dx, and if we do the calculations from the previous example, you can see that we end up with 1 over 4 times x to power 4, but from -1 to 1 for this example, because interval is different now. So if we calculate that, then we're gonna have 1 over 4 plus 1 to power 4 minus -1 to power 4. And if you calculate this term here, you end up with just 0. So that means that the inner product of f1 and f2 is 0, and by definition then we can call f1 and f2 to be orthogonal on the given interval. This is again very important. Interval on -1 to 1. Because you remember from the previous example, we found f1 and f2 to be having a non-zero inner product on the interval 0 to 1. So from the first example, the inner product of f1 and f2 was 1 over 4 for interval 0 to 1. From the second example, we saw that the inner product of these two functions was 0 for the interval -1 to 1. That's another beautiful example that shows that two functions can be orthogonal on a given interval while they are not orthogonal on another one. So in other words, it's kind of more clear that there is no really geometric significance when we talk about the orthogonal functions. It's just a definition. It's just a mathematical expression that turns out to be very important when we want to solve the partial differential equations.